What happens if I have two waves of opposite phase come towards each other? Let's sketch that series of diagrams. Again, a time-lapse view. There's the equilibrium position. I have a crest that's traveling to the right that I'll call crest C. And at the same time that somebody on the left side of the spring is shaking a crest, then somebody on the right side of the spring is shaking a trough. We'll call that D. And now crest C and crest D are going to approach each other. That's the snapshot that happens before the two disturbances overlap in the middle. Let's take a look at what happens during the overlap. When C gets to the middle, it tries to make the medium go up. When D gets to the middle, it tries to make the medium go down. If these happen to have the same amplitude and the same wavelength, then there will be a brief instant in time in which the crest will fill up the trough. Or you could likewise say the trough destroys the crest. So that for a brief instant in time, the medium completely shows no pulse at all. Where did the energy go? Well, the energy is all tied up in tightness of the medium right there where that overlap has occurred. There is tension that's there that's not in the rest of the medium. That energy is still there, but the appearance of the material is that there is no disturbance, either up or down, if I have equal amplitudes and equal wavelengths. That occurs only for an instant in time. All right, what happens afterwards? The same thing as what happened in constructive interference. We're going to call this destructive interference. The two pulses are going to continue moving in their original direction as if they never encountered each other. And if there's no friction at all, then pulse C is going to have its original amplitude and wavelength. Pulse D will have its original amplitude and wavelength, and they'll continue on in their original directions. So there's my equilibrium position. Pulse C continues to the right, pulse D continues to the left, and we call this situation destructive interference because during that brief instant in time where those two pulses that are out of phase with each other overlap, they destroy the amplitude of the wave. So let's go back to our simulation again. We've got our simulation where I have incident waves coming down from this side, the left side. They're traveling down. Crest, trough, crest, trough, crest, trough, crest, trough. The energy is traveling down towards the right. It gets to the end. There's fixed in reflection. There's a phase shift. And what happens is that I get a series of waves traveling to the left. Trough, crest, trough, crest, trough, crest, trough, crest. Those pulses interfere with each other, and I end up with something called a standing wave. Over a period of time, if I take a time-lapse photograph, then what I end up with is a pattern over time that's swept out and looks something like this. These parts have names, and we want to label those names. First of all, let's sketch the equilibrium position. If there were no disturbance at all, the medium would be sitting along that line there. There are places where there is destructive interference occurring. We call those places, such as here and here and here, we refer to those as the nodes of the wave. Singular is node, plural is nodes. There is destructive interference that's occurring at those points. But there are other points that have large vibrations, such as here and here and here and here, and we refer to those as antinodes. And the antinodes are the points where constructive interference is going on. One thing that's going to be important in these diagrams is to recognize what distances represent a single wavelength. And so I want to mark those on this diagram. Starting at the left side, if I start here and I go for one complete crest up like this and one complete trough down like this, that distance along this wave here is considered to be one wavelength. And so one wavelength for a standing wave is going to include two complete antinodes. So that pattern there that has one complete crest and one complete trough is considered a single wavelength. That's going to be important when we get to standing waves in pipes and standing waves on strings, and we're talking about harmonics of wave systems. We can talk about standing waves on strings, standing waves in pipes, and musical instruments are built in such a way to take advantage of how it is that the frequency or pitch that we hear is related to the length of the string, in the case of a violin or a guitar, or the length of a pipe, maybe in a flute or a trumpet. All right, so now a lot of water has flowed under the bridge, and we want to actually work some numerical problems. This is from problem set 23, it's number 1. An ocean wave travels with a speed of 2.5 meters per second. What is the wavelength of the wave if an ocean buoy bobs up and down 12 times in 10 seconds? First, determine the frequency of the buoy. Well, what are we trying to find? The wavelength. So we know what the speed is. We're looking for lambda. So we know what v is. It's 2.5 meters per second. If I could figure out a number for the frequency, I would be able to substitute it and figure out what the wavelength is. Well, what do we mean by frequency? Frequency is the number of vibrations per second. What do they tell me in this problem? They tell me that an ocean buoy bobs up and down 12 times. Well, this is a transverse wave, and the up part would be a crest, and the down part would be a trough. So I get 12 vibrations in 10 seconds. That's going to be the frequency. The frequency is 12 vibrations in 10 seconds. And I can do that in my head. Vibrations per second is a unit that we call hertz. 12 vibrations per 10 seconds is going to be 1.2 hertz. So now I've got this problem linked. I know a number for V, it's 2.5. I know a number for F, it is 1.2. I put the numbers into the wave equation and I solve the problem. Alright, so now I put the numbers in my calculator and I get 2.083 repeating. 2.083 watts. I've got meters per second upstairs, I've got hertz downstairs. Well, a hertz is the same thing as a reciprocal second. So let's take a look at the units. Meters per second divided by hertz are equal to meters per second divided by reciprocal seconds. And you know how to clear a denominator. You multiply the top and the bottom by the reciprocal of the denominator. So I'm going to multiply the bottom and the top by seconds. So downstairs I have 1 over seconds times seconds, which is equal to 1. Upstairs I have meters per second times seconds. Well, this second downstairs and that second upstairs cancel each other, and the units I'm left with are meters, which is what I want. It makes sense. It's a distance that's being measured. 2.083 meters. If you're dealing with sig figs, then you would want to round that probably to 2.1 meters, but I'm not worried about sig figs at this point. I'm more interested in, do you know how to do the problem? Next problem, 23.2. A transverse wave traveling through a coil is represented in the diagram. The frequency of the wave is 5.5 hertz. You've got several things that you've got to find. A, the amplitude, B, the wavelength, C, the period, and D, the speed. This basically tests, do you know what the different parts of a wave are, and can you look at a wave diagram and tell what the different parts are? I'm going to look, and for amplitude, I'm going to look at this number right here. And I remember that amplitude is the distance from the equilibrium position to the top of the crest, or from the equilibrium position to the bottom of the trough. Well, if that total distance is 75, then the amplitude is going to be half of that. 75 divided by 2, which looks like it's going to be 37.5 centimeters. That's the amplitude. That's part A. Part B says, find the wavelength. Well, to find the wavelength, I'm going to look at the distance from the beginning of one crest to the beginning of the adjacent crest. And it looks to me like that they've shown a distance here from the top of a crest to the bottom of a trough. And that turns out to be half a wavelength. I'm going to take that number and multiply it by 2, and what I'm going to find is that the wavelength is 2.4 meters. There's my result. Part C says to find the period. The period is the reciprocal of the frequency, and they've told me what the frequency is. They've said that the frequency is equal to 5.5 hertz. So I'm going to take the reciprocal of that. The period, T, is the reciprocal of the frequency, and I put the numbers in. And I get 0.18 repeating seconds. That's part C. Now for part D, the speed of the wave. Well, I can go to my wave equation and say that the speed is equal to the wavelength times the frequency. Or I could say the speed is the wavelength divided by the period. And I happen to know what both of those numbers are. Since they gave me the frequency in the problem, then I'm going to use that one. I know what the wavelength is by looking at the diagram, and so I can solve this. The speed is the wavelength times the frequency, and now I'm going to put in the numbers. And I get that the speed is 13.2 meters per second. So that brings us to the end. There's a lot of vocabulary. A lot of these things are review. We want to solidify them over time because we're going to use them to help solve problems.